Hello everyone, this is going to be section 2.7 in the derivative as a rate of change. So when we were talking about limits, we kept using in the definition the idea of the secant line and going to the tangent line. And this is the reason why we were using that particular example. When we have a function, we can identify the slope of the tangent line with the instantaneous rate of change of a function. And so the slope of the tangent line and instantaneous rate of change is going to be negative when you see that the tangent line is doing this movement, and the slope of the tangent line and instantaneous rate of change is positive if you see that it's going in this direction. Okay, and we can think about this as the change along the curve, and these values that the slope is going to have is going to give me a new function that I call the derivative. If we look more ahead, if a curve is representing the trajectory of a moving object, the tangent line of a point in the curve indicates the direction that the motion is taken in that point. So for example, here we have this curve over here, and we can see that the tangent gives the direction of the motion that we're taking. So for example, it's moving in this direction, and so that's why we have that the tangent line is doing this, then it changes to this, and over here is going to change to this. But it classifies heavily the direction of the object. Now, these quantities, they have important geometric interpretation. As you can see, we're transitioning from the average velocity given by taking 2 points and calculating the slope of the secant line, and this is giving me the average velocity, and then later when we get to the tangent, then we're transitioning by doing the limit, by taking the limit when we're approaching so close that it's not a secant but a tangent at that point. And so the velocity of the instantaneous velocity is equals to the slope of the tangent. Now, thanks to that, we can describe a little better how the movement is going to behave. One example will be calculating here instantaneous velocity and given a specific function. So for example, a rock is launched vertically upward from the ground with an initial speed of 96 feet per second. The position of the rock in feet above the ground is given by the function s of t minus 16t squared plus 96t. So now we're considering the point 180. So when we plug in t equals 1, we're going to get s of t being 80 on the curve, and we want to check what the instantaneous velocity is going to be at that point. So one way of doing this is calculating what the slope of the tangent line is going to be at that point. Okay, in this case, that is going to be 64. So we can also say that the slope of the tangent line at that point is going to be 64. And so how did you calculate really this tangent line in here? Well, you can get the point that you're using and use another point that is directly over the tangent line to calculate the slope. And so you use the equation of the slope to calculate that. But it would be nice if we could use the function itself to calculate the slope of the tangent line. And that's what we want to do with the derivative. So in general, if we consider a curve f of x and the secant line intersecting, we know that what we need to do is an approximation to obtain the tangent line from the secant lines. So the slope of the tangent line is going to become the limit when we're approaching the point. Let's say the point is A. So when x is approaching A, when we're moving towards A, of the secant slope, which is f of x minus f of a over x minus a. This difference, f of x minus f of a, is the change in the value of f on the interval ax, and x minus a is the change in x. So it's always the change in the function over the change in the domain. Now, what's happening here, remember, is that if we zoom a lot, when we're getting closer and closer to the function, zooming out, there's no difference between the tangent line and the function. So we can approximate the tangent line via the function, okay? Or backwards also works. We can approximate the function via the tangent line, okay? This is something that we're going to explore later when we want to make approximations to a curve. But for now, this notion is just going to help us define the derivative. So again, and just to summarize, the average rate of change, as we saw on the introduction to limit, is related to the secant line, and it's just the difference between the values of the functions over the values in the domain. And the instantaneous rate of change is just going to be the limit when we take the difference of those 2 points and we make it as close as we can. Okay, and so that produces a tangent line. Now, given that we have now our tangent line and we're using the point A, f of A, we can actually find out what the tangent line is. And we can use the equation of the line, y minus y0, using f of A as y0, equals the slope, which we use the slope of the tangent line, x minus x0, where x0 is A. Okay? So this equation is going to give us the tangent line equation at a given point that we want in particular. So just to do an example of this, so let's find the equation of the tangent line to the graph of f of x equals 3 over x at the point 2 3/2. Okay? And so let's do this on the board. So notice that we're saying, well, if I plug f of 2, notice what happens. This is 3/2, and that's why we have the point 2 3/2, and this is a f of a. Okay. So now what we like is to calculate the limit when x goes to 2 of f of x minus f of 2, x minus 2, which is the change in the functions over the change in x. So now f of x is going to be just 3 over x, and this is going to be 3/2 over x minus 2. Okay. And so now I'm going to do some, I'm going to put this fraction together. This is going to be 6 minus 3x divided by 2x, and everything is going to be divided by x minus 2. And this is going to be limit when x goes to 2. Now this is equals to limit when x goes to 2, and I'm going to put a 1 here and multiply this with this and this with this. And so this is going to be 6 minus 3x divided 2x over x minus 2. But I can probably factor a 3 from here, as you can see. Actually, I'm going to try and factor minus 3. So if I factor minus 3, you're going to see this is minus 3. And so I'm going to get, since I'm factoring a minus 3 from here, it's essentially divided by minus 3. So 6 divided minus 3 minus, so this is a plus because I factored this out. Notice that if I multiply this back, I'm going to cancel this minus 3 with this minus 3, and I'm going to get the minus 3x in here. So you can see there's no change. Now, now next, I simplify. 6 divided minus 3 is going to be minus 2. And so now you can see that this is minus 2 plus x, which is essentially the same that x minus 2. So these two things, they can cancel each other because they're the same thing. Okay? And I'm going to get limit when x goes to 2 of minus 3 over 2x. And that's going to be minus 3 over 4. Okay? And remember, this is the slope of the tangent line at this point. So if I want the tangent line, now it's going to be using the equation of the line, which is this. I get to replace using the points that I had before. Y minus 3 halves equals minus 3 over 4, x minus 2. And so this is our equation of the line. I can simplify this, of course. This is y minus 3 halves equals minus 3 4x. And multiplying this here is going to give me plus 3 halves. And so this is y minus 3 over 4x. And I add this to this. So it's going to be 6 over 4. So, sorry, it's going to be 6 half. 6 half, and so that's 3. So minus 3 over 4x plus 3. And so that's exactly what we're going to get in here. Notice we get y equals 3 over x, and then we get that the slope of the tangent line is obtained to be minus 3 over 4. And we get that the equation of this line that is tangent at this point is that. Now, the process is not possible if we didn't have before the notion of the limit. We need to have that approximation first. And so another way that we can make that interpretation now is, well, we want to approximate at a point A. And so what we're going to do is we're going to move a little bit after A. So we're going to move to the point A plus h. So 8 plus a little bit something. And then what we're going to do is we're going to reduce that h to almost nothing. So we're going to make h go to 0. So they get closer and closer as they can. So now I can replace, instead of using the formula of f of x minus f of a, x minus a, I'm going to replace x by a plus h. And so if I replace x, well, let me do that in the formula. So you can see there is equivalent. If I have f of x minus f of a, which was my initial quotient, but now I'm replacing x by h plus h, this becomes this. And so notice a gets canceled with minus a, and it produces the simplified formula. And so notice that making the limit when x goes to a is equivalent to making the limit when h goes to 0. Okay, so the two formulas are equivalent, and we can get the derivative with any of the two. Now, the average rate of change on the interval a plus h can be related to that formula with the formula of the secant slope in that way. And we can also define the instantaneous rate of change as the limit when h goes to 0 of the same formula. So this also provides the slope of the tangent line. Now let's make another example here and find the equation of the line tangent to the graph of x cubed plus 4x at the point 1, 5. Okay, so we're going to get, and now you can see here that the line is going to be 7x minus 2 on the point 1, 5. But let me show you how you get to that point on the board. So again, we start with the function. We start with f of x equals x cubed plus 4x, and then you want to calculate the slope of the tangent line at 1, 5. So notice that when you plug in 1, you get 5 in here. So this is a and f of a. Okay. So now let's use the limit that we got taught. So we limit when h goes to 0 of f of a plus h minus f of a over h. Okay. But now we're using the point that we get. So a is equals 1. So limit when h goes to 0, f of 1 plus h minus f of 1 over h. So who's 1 plus h? Well, let's plug that in the function. That's going to be limit when h goes to 0, 1 plus h cubed plus 4, 1 plus h minus f of 1, and f of 1 we know is 5, divided by h. Okay, so this limit, if you take it right away, you're likely going to get a 0 over 0 situation. So you need to open up this limit, because in this way, if you get a 0 in the below and you get a 0 above, that's not going to fly. So the way that we work with this is we open up this cube situation. This is going to be 1 cube plus 3 times h plus 3 times h squared plus h cubed. And that's opening the binomial cube, plus 4 plus 4h minus 5. Notice that we have 1 and we have 4 and we have minus 5. So this is going to cancel there. And then in the next step, we get to add up things that are similar. Notice this is 3h and 4h. So we can have h cubed plus 3h squared plus 7h. And everything over h. But now we have h on top and bottom that we can factor out and cancel out. So h is a factor of h squared plus 3h plus 7 over h. This goes away, and this is the limit when h goes to 0 of h squared plus 3h plus 7. And if we plug when h goes to 0, this is going to go to 7. So here, what we get is that the slope of the tangent line is 7. Okay? And so the equation of the line, y minus y0 equals mx minus x0, can be replaced by y minus 5 equals 7x minus 1. And so this is y equals 7x minus 7, and then plus 5, which is 7x minus 2. Okay? So that's the way that we can use the limit of the tangent line to obtain the equation of this line. Now, we can generalize this idea and talk about a function in a point. So we're going to talk about the derivative of f at the point A. And so now that slope of the tangent line is going to be called f prime of A. So the slope of the tangent line at the point A is going to be the function derivative evaluated at the point A. And it's going to be given by any of the two limits that we previously introduced, and I showed the examples. So with either f prime of A being equals to the limit of x going to a of f of x minus f of a divided by x minus a, or using f prime of a as the limit when h goes to 0 of f of a plus h minus f of a over h. If any of these two limits exist, and of course if one exists, the other one is going to exist as well, we say that f prime of a exists, and we say that the function is differentiable at that point. So it's differentiable at the point A. Now let's do another example, and let's compute in general. Let's compute what happens when we compute f prime of 2. So you can pick in here whatever function, whatever limit you want to use, and then after that compute the value of the derivative of x equals 2. So again, let me show you this on the board. And this limit is nice for the points, but it depends on whatever you want to use. In this case, again, I'm going to go ahead and use another the other formula just to show the example. We want to find out what f prime of 2 is. So I'm going to use a limit when x goes to 2 of f of x minus f of 2 x minus 2. I could use the other one, there's no difference, but I'm going to use this one. So f of x is going to be square root of 2x plus 1 minus f of 2. And f of 2 clearly is a square root of 4, which is 2 plus 1, so it's going to be 3. And x minus 2. So clearly the issue is that we have an x minus 2 here. And this is not going to go well because it goes to 0. So we need to do something else. If we plug 2 on the top, you also get a 3 minus 3, 0. So we need to do something, conjugate the limit so we don't get that. So we have initially this term. And we can rewrite that, right? So we can just write this as square root of 2x. And this plus 1 minus 3 minus 2 in this way. And then what we're going to do is we're going to use a difference of a square situation. So we're going to multiply by square root of 2x plus 2 over square root of 2x plus 2. So we're essentially using conjugate technique. We'll multiply them by 1. And now if we do that, then we're going to get the difference of the squares. So square root of 2x squared minus 2 squared. That's what we get on top. And on the bottom, we get this. Now, the bottom is not something that we really care at the moment, and that's fine. Here, when we used the difference of the squares, this is going to produce 2x minus 4. And so notice that that is immediately going to solve my issue, because I can factor what I need to cancel. So I can factor 2 here, and I get x minus 2. I have x minus 2 below. And so I get to cancel this and this. So notice that at this point, it requires that you have a good ability with limits to be able to compute with all the techniques that we had in limits. So that's why we actually introduced limits first. And so we have 2 over 4, and we have 1/2. And so at this point, we find out what f prime of 2. Okay, f prime of 2 is 1/2, and now we use the 2 points, 2 and 3, and we can calculate this equation of the tangent line in there. Okay. One more example. Let's calculate f of x equals 3 over 4 pi x squared, and let's compute what f prime of 3 is. Okay. In here, the difference is I use this formula now, so I'm going to use the other formula just to make an example with both of them. So f of x 3 over 4 pi x squared. And we want to compute f of 3. So let's use limit when h goes to 0 of f of 3 plus h minus f of 3 over h. So initially I go for the function 3 over 4 pi 3 plus h squared minus f of 3 for pi times 9. So it does need quite a bit of simplification. I can remove this 3 over 4 pi out of the limit, since it's the most complicated constant, and I can just put it out, and now this is going to give me just 1 over 3 plus h square minus 1 over 9 over h. And then that simplifies a little bit the fraction. Now I do exactly the same thing that I did from before. This is going to be 9 minus 3 plus h square over 9 3 plus h square. And this is going to go over h, right? So immediately I'm going to skip a step and put the h right away in here, since that's not going to make a difference. Normally we'll be putting a 1 in here. Now this is going to be the part where I open the squares. So this is 9 plus 2 times the first by the second, 6h plus h squared. So you can see in there that I'm going to lose the 9. 9 is going to get canceled, and I'm going to get minus 6h minus h squared on the top, and on the bottom 9 plus 3 plus h squared times h. Let's not forget the constant outside. And so now with the h factor, I can do minus 6 minus h, and the h over here, 9 3 plus h squared. I get to cancel this. And so now it's not going to be a 0 over 0 situation anymore. We get that this is going to be minus 6 minus h, and 9 3 plus h squared. We're going to plug now on h equals 0. And so this is going to be 3 over 4 pi times minus 6 over, and then here below, this is going to become a 9 as well. And with this 9 is going to be 81. All right. And then I can simplify everything in here. This 3 by 6 is 18. And well, I can see that 6 is 3 by 2, right? And so this is a 9 and a 9. And so I can see this is a minus 2 left. That's going to cancel with one of this here. So on the top, I'm going to have minus 1 over 18 pi. That's what the end result is going to produce with a little algebra. And so from there, we can see that that's precisely the rate of change that the sound intensity function is going to have over here for this, and which is the function that we're using, and we can get the slope of the tangent line. So this is going to be the end of the first part of derivatives. Now next, in part 2, we're going to see more examples of how to calculate this type of limit.